that you've had a prior stat course. Stat 100, AP Stats, Stat 400, any prior stats course that you know some statistics. So the other section starts from square one. The other difference is that this section also is linked to a independent study on R. So if you're interested in learning the statistical computing language R, this is by far your best bet if you want to take that independent study, which is a very serious course and it's going to take a lot of work. It's basically a real course, but it's an independent study. And you get 2 hours credit for it. So please, I don't want to spend time here discussing it, but anybody who's interested, particularly if you have some computer science background, you should just check that out and register for it. And it goes along with, it covers the same topics that we cover in class here without using R. We'll have bonus exercises on R and introduce it, but it doesn't, we don't teach you the language. All right. Now, the other thing I should tell you is that Stat 100, the current Stat 100 and Stat 200 are really linked. We're basically just the same, it's the same method. So it's a nice, if you've taken Stat 100 here on campus, this should be a little bit easier for you in terms of a lot of the concepts. Now, many of you haven't. So what I've done that I think will help, this is new this semester, what I've done is put a bunch, for the first 2 weeks, where the concepts that you really need, the concepts, you know, just what a z-score is, the normal approximation, what hypothesis test is, the difference between how you get, what a confounder is. All these concepts that we really emphasize in Stat 100, well, maybe you've taken another course that hasn't really covered those very well. So what we're doing is we have these bonus review exercises. They're up there now, just for the first part, for part 1 in the notebook, on type 1, type 2 errors in power. You need to get down what a z-score is, what a hypothesis test is, what a probability distribution is, etc. So those are very simple pre-lectures from Stat 100. So if you've taken Stat 100, they're the same thing you've already taken, but you've already had before. Very simple pre-lectures. You'll be doing them again. And they are for bonus credit. So that's where we're starting. We're going to do the same thing when we hit correlation, causation, confounders. Very difficult concept. You can't hear about it too many times. And we're starting with very simple explanations that will give you a solid foundation. So everybody should do those bonus exercises. They're fun. They're easy. All right. So I think that will help. Now, what else should I talk about? I expect okay, let me talk about, we don't have a lot of time today, but we don't have a lot of time to go over the syllabus because I want to jump right into the lecture. And I think you guys already, you can probably explore the syllabus yourself. But I want to emphasize one thing, that this calendar right here has all the other information except for grading. It tells you when everything is due, when our exams are. So right here, this is just some review stuff you can look at. But right here, we are going to be talking about Part 1, Type 1 and 2 errors for this week. And on Friday, you have 2 things due online Kappa. So you should just try to get online Kappa right here. And these are both bonus a survey that we analyze our own data just like you did in Stat 100. It's really fun to do. And then bonus pre-lectures from Stat 100 that we are now using as review exercises. Those are both due Friday, but honestly, you should do them as soon as possible because it will help you understand Thursday's lecture and even today's lecture if you go home and do them. All right. So then all the homework is due on Mondays and Wednesdays. Homework is done Monday and Wednesday, online Kappa at 11:59 p.m. Now, here's something you probably haven't seen before, and that is that I am going to post as soon as class is over. There's cameras here. I have all different ways to do this. We are going to post this lecture right now within an hour after class or an hour and a half after class, if no technical glitches, right here. So everyone, the in-class people and the online people will be getting these lectures. But you guys can go back. Let's say, who can concentrate for 80 minutes without, and you're writing stuff down? Come on, this stuff is not so easy, a lot of it. So you have the advantage of being able to go back and say, now what did she say? How did she work out that problem? To go back and make sure your notes are correct. And, or if you're sick one day, or if you're just spaced out or distracted, and certainly while you're doing the homework. People tell me over and over and over again, I understood when you were doing it in class, but now that I'm doing the homework, I can't quite remember. Well, that happens to everyone. So here's a way where you can say, okay, I understood in class, let me see that again. So you can go back and get the lecture a second time. Now, we are going to have, I really love this full classroom. I think there's a nice energy with that. And and a lot of people feed off that, need social interaction. They work better. They learn better. They get that excitement going. So I really encourage you to come to class. You can ask questions. We can interact. And with that in mind, I'm giving people in the in-person class the iClicker points. Now, people who are listening to this online at home, don't worry. You have equivalent bonus points. You can just look on the bonus grading and you'll see them. Okay, so they're going to be for doing our bonus exercises. You'll get additional points. So I want to keep the two groups as alike as possible because, and you're going to see why in this lecture, because, well, first off, let me start by saying this is a super exciting time to be learning data analysis because you know it's used for everything. So everybody wants to learn it, right? Everybody understands its importance, not only in terms of job opportunities, but in terms of interpreting everything in the world, understanding, making decisions under uncertainty, just being educated. It's a new reading, and at every level, you need to understand it. So that's real exciting for you, and it's super challenge for me because I really want you to understand it, not just the technical jargon, but be able to apply it at all levels. So the exciting thing for me is to interest everybody in a data analysis project. And we've got an incredibly cool one happening right now. This analysis, this online versus in-class comparison. Which one works better, right? I want to keep everything the same. The only difference being that you see the lectures online or in person, so that any differences in the results as measured by your overall course average, right, at the end of the semester we can analyze. Is there a difference at all or not? And if there is, what can we attribute it to? Now, we already have last semester's data from Stat 100, so we can even look at some of that today. But it's a great way to see how complicated real data is, and also to be able to actually help people, because if we can figure out what's going on, we can help the university advise students on which course would be best for them. Because I imagine, like most things, that it differs depending on different people. So we want to try to get at which groups could benefit by the online, which groups can benefit by the in-person. And it's very exciting because the provost has funded this research project, and we even gave a talk about it at the Data Summit. And there's a lot of interest. And I want your help. I need your help. Because who understands motivations more? Who understands what's going on better than the students themselves? And so I think it's super important to involve students in analyzing data about stuff that matters to them. I don't think we can do it ourselves because we don't understand the psychology as much. So you do. You'll know what questions to ask. So I'm going to ask for your help on anonymous survey data. Everything's protected. Don't worry about that. It will all be, this is privacy of data is extremely important. So this data, some of these surveys that we do are going to be used with that in mind. And you'll get credit for turning in the survey, but we can't tell who turned in which survey. We can't. So we have to you'll understand the difficulty of analyzing data under real conditions, because you're going to be a part of it. So it's a hugely exciting project, and I'm just really excited. I just hope I can get all the ideas across. So any questions on what I've talked about so far? Now, let's just get to the brass tacks of the nuts and bolts of how you can succeed, get the good grade in this class before we go on. So let's just make sure we got the grading down. So let's look at that. All right. So there's the same exams for everybody. They're in class. We hand grade them, which is a huge advantage for you because we give you partial credit for showing your work. The final exam is the same way. It's hand graded too. I might change that because there's a lot of people in this class, but I want to keep it that way. All right. So first question everybody wants to know, do I curve? Because here's the grading scale. Well, it's a good question. I will never curve down, meaning I will never say if everybody does well, I'm not going to say, well, everybody did well. I only want to give 20% A's or something like that. No. But would I curve up? Yeah. If I write a really bad exam and people bomb it, I will curve up. But that doesn't usually happen. All right? I try to write exams that are fair. So now here's all these bonus points. These are ways to encourage you to do things, encourage you to do things I think you should do anyway. So here, the first two I've already talked about, the long campus surveys. You get bonus points for that. The review exercises, iClickers, I've already talked about that. All right, now, this is for the in-person only. Now, for the online, so everybody has this. You can, as I said before, you can, if you're serious, you can do this R independent study. But, and if you want to, of course, I encourage everyone to do these bonus R exercises. And the idea is instead of learning how to program in R, you're going to learn it as more of a command language, how to do the same exact problems that we're doing already using a very easy point-and-click data visualization program and doing by hand, knowing how to do these by hand. You're going to do those same problems using R. So you'll see that they agree. So you're just going to learn it more as a command language. You do these commands, you can get some plots, and also doing some cool plots that we can't do otherwise. So, and it's fun. So those are the R exercises. And then, but there's no attempt to teach you how to program in R or you can't possibly do that unless you spend hours and hours. All right, and then the last thing I want to talk about is the single most best pedagogical tool that we've found to teach large lectures, and that is this notebook here. And especially for the online, for the in-person, it's a way to not forget that with math, paper and pencil is your friend. You can't just start clicking on things. You need to be able to draw pictures, work out equations. To do it, I mean, all research shows this for math learning. It's by far, there's nothing that can replace it. So the motto here is in learning statistics, like learning language, learning anything that you really want to know, you've got to learn it at all levels. You can't forget about the simple everyday language, the way people learned, right? And also, we have to learn technical jargon, math, the whole higher. We're trying to integrate it all, make you trilingual, quadrilingual. Lingual, understanding the concepts in everyday language, understanding them with technical jargon, and understanding them mathematically, to some degree. Okay, because this does not have a calculus requirement, so we're not going to be doing any calculus in this class. But I'm going to try to give you an intuitive mathematical feel for most things. Okay, so that's the idea. And so far, stop me if you have any questions. Okay, so that's the grading. How are they figured into your grade? Well, they can only help you. In other words, you can get 100% without doing a single bonus assignment. A single. You don't have to attend class. You don't do any of these things. If you get the required work, if you got 100% on all the homework, the exams, and the final, you'd get 100%. Now, with the homework, the idea, here, it's on the syllabus. This is important, too. It's not only the calendar, but you have to read this. The calendar is throughout the semester. It's important. This, familiarize yourself with it. Read it 5 times. Okay? And you'll see right here, no late homework accepted. It's LonCap. It's graded on LonCappa, immediately graded. And it's not like hand-graded stuff where you used to turn in the homework, and if you're 2 minutes late, it's all 0. No. If you're a second late, yeah, what you haven't turned in yet will be marked 0. But if you've done 70% of it, of course, that will be graded. So we do drop your 3 lowest homework scores. So please don't email me if everybody has emergencies in their life. Everybody, If you want to blow off 3, look, don't worry about it because your 3 lowest are going to be dropped. All right? So we don't have to spend a whole lot of time dealing with excuses and so forth. Just know something, you have an emergency. Well, everybody else, look at the size of the class and look at all the people on. People have emergencies, and this is why we do this policy. All right, so makeup exams, that is the other thing. So we will go to the exam schedule now, and it will tell you more about the exams. Here's where the locations are going to be announced. But right now I want to tell you that there's 3 evening exams. So mark these in your calendar. And conflicts are given the same day at 4:30. And if you can't make either of these exams, there's a conflict. If you have, anybody can sign up for the conflict. Just because maybe you don't like to take evening exams. Maybe you just don't want to. Anybody can sign up for those at 4:30. But let's say you can't do either of those. Well, then you do have to talk to me, and show me why you can't do either of those. Me or David Collier, you want to stand up? He's going to be helping me with organization, technical stuff, and so forth. He's our technical expert and also organizes the courses for the intro courses. All right, so you can email him, and he'll set you up with a conflict. Usually it will be 6. Well, I'm not sure for this, but we'll figure something out. Okay, and final exam, online courses have no assigned time, so as soon as the university tells me, I'll tell you, and they usually give me a choice, and it's during finals exam week if you're online. You guys, you know when yours is. It's right here. And I'm going to announce the location. I haven't been assigned it yet. So conflicts for this, you have to look at the university policy. You have to have an actual conflict to take it at a different time. So that's when your exam is. Any other questions so far? Yeah?
What is the 100 bonus points relative to points in the class?
Yeah, that's the 100 bonus points are not just tacked on. What they are is there's a formula, a scaled formula. You can look at that formula. So basically, we can look at it for, let me just go up here. I didn't really review it that well. I'll just show you right now. Okay, so what do I say down here? Okay, so they're figured into your grade like this with this formula here. So what does that mean? So let's say that you got, suppose at the end of the semester you have an 80% average after averaging all this, right? This adds up to 100%. So you have an 80% average. Now, what if you did all the bonus points? Well, that would be 80, or what if you did 90% of the bonus work? That's what I have here. That would be 80 plus 25% times 90 over 100 plus 25% over 90, so you would get an 83.67. Okay? Does that answer your question? Good. Any other questions? Yeah? People in the online section are very welcome to attend lectures. Is that your question? Oh, yeah, you got to attend the midterm. You've got to attend. People in online, most of the people online are on campus. For those who are off campus, if anybody out, like a handful of you, you'll be taking the exams, the same exams online using ProctorU, and that's on our Compass site. But that's only a couple of people. If you're on campus, you'll be taking the same exams, the midterms, the same times. And I do have assigned rooms for that. Okay, so it's exactly the same time. Good point. Any other questions? Anything else about the calculator? You can use a calculator on any exam, any type of calculator, but you're going to have to show your work. You can't program your calculator with formulas, etc., but you can use calculators on all your exams. If you don't have a fancy one, I don't recommend spending the money. You can use a simple calculator, unless you have to spend it for another class. What else? So I strongly recommend that everybody get the notebook. We're going to be filling it in class. You're going to see in a few minutes. We're going to start that. Anything else? Oh, yeah?
For the independent study, do we need to have that figured out if we're going to do that by this week or something like that?
No, I think with the independent study, there isn't. You can. What I would do, if you want to look at the independent study, is you basically can try it. You can look at it, and You could try, the first 2 weeks there's not much to do. You could sign up, you could drop out. You can just sign up, drop out if you want to, you know, try it, see if you like it. I mean, if you're looking at the independent study, my strongest recommendation is to read these frequently asked questions. Like, how much time do I have to spend on it to get an estimate? Because people think independent study, I don't have to spend any time on it. Well, we have data on all this, and people are spending a lot of time on it. And they're probably even under-reporting. Okay, so and then, you know, just read about it and read those frequently asked questions from students, because it will probably answer your question. Okay? Yes? For honors, there's nothing for honors. We just don't have the time to, unfortunately, we don't. So we just have this independent study. Talk to me if you really have a really cool honors project you want to do. Okay, anything else? Okay, so if you're here, you can get back to Stat 200 this way. All right, so why don't we just dive right in and let's go to the document camera and start the first lecture. And I'll try to let you out. You're supposed to, at 10 minutes early, so those of you who have individual questions can come up and ask them. All right, so this class goes till 2:20, so I'll try to let you out at, no, it doesn't go to till 20. It goes to 3:20, right? 3:20. Is that clock right? We should get this, yeah. Right? Let me see. I have a tendency to run over. I don't want to do that. Yeah, it's good. Okay. So let's all start on page 1 here. And part 1 is on significance tests, p-values, type 1, type 2 errors, and power. All right? So let's look at, first of all, how many people have a notebook, do not have a notebook right now? You don't have a notebook. All right. Well, you're going to see this video. Let me see if I can get it really better so you can read it. And if you can't see it, how about you just come on down closer if you don't have the notebook right in front of you? Because, okay. But just mostly listen. I think we'll be fine without the notebook today. All right, so as I say here, a significance test, it's also known as a hypothesis test. So let's write that in. Those are interchangeable. A hypothesis test, a significance test, is a statistical check to determine whether some difference you observe is real, meaning due to a particular cause, or just due to chance variation. And the null hypothesis is that it's just due to chance variation, that it's not very interesting. We abbreviate this null hypothesis, H for hypothesis, and a little 0 down there for null, and think of it as the dull hypothesis as a way to remember it. And it's just that whatever effect you see is just due to random variation. So the population parameter is a particular value, and any observed sample difference can be explained by chance variation. It's generally the hypothesis of no or null effect. No or null effect, okay? For example, if we were going to do, let's put our current experiment in the context of a hypothesis test. And what we would say is what? That whether the online or in-person teaching method makes no difference. People learn the same regardless of the teaching method. That the null would be it doesn't make any, the two groups are basically, the teaching method makes no difference within random variation. Any difference we see in the results at the end and the scores between the two are just due to random variation, okay? Now, the alternative hypothesis, abbreviated by H for hypothesis and A for alternative, is the hypothesis that there's something else. There's a systematic difference between those two groups, that they're not the same within, that there's some particular reason for it, okay? That there's some other reason besides chance that explains the sample data. It's the hypothesis that the effect was real, meaning due to some systematic difference. Now, that difference doesn't necessarily have to be the online versus the in-person teaching, except in, certainly in observational data, there could be plenty of differences between the people who choose one version or the other. But there is a systematic difference, okay? So now the whole argument is an argument by contradiction, and it's confusing to people because of all the double negatives, all right? So what do? We assume this null dull, that there is no difference between the two groups in the population, this idealized population. Like if we did this again the next semester, there's no difference. That the difference this semester is just due to chance variation. And if we did it, it won't hold up, right, if we repeat it again. So you think of this idealized larger population, and the null is that in that idealized we might see a little difference in our sample, what we're doing now, but in an idealized larger population, there is no difference. So this difference will not hold up. That's the idea. And you assume that to be true, and then you set up a simple probability model, where often the simplest type is a box model, drawing randomly from a box that have numbers written on them. It's basically you set up a probability model, right? That it isn't, if you're talking about random variation, which is what stats is all about, well, you have to define the random aspects of it and come up with a probability model based on translating whatever you're interested in to what parts of it are random, and then test that. Okay, this is the idea of a hypothesis test. So we'll ask then if the results you found were very surprising, if the sample was randomly drawn from that box. Okay, so then what do? Then you pick a statistic. Like in Stat 100, we've mostly been looking at z-stats, but t-stats, chi-square stats, f-stats, I guess not. But those are the stats we'll certainly be looking at. Lots of different types of statistics, test statistics, for which you'd expect the null and alternative hypothesis to give different values, right? You could pick the sample mean, right, or the average, and then that would translate into a z-statistic or a t-statistic, to see if it's outside the range you'd find just by random sampling from the null box. So you make a version of that statistic. Sometimes you have to change the statistic that has a known sampling distribution so that you can figure out the likelihood that you'd see such a big difference just by the luck of the draw. So, for example, if you're using the mean, it would be the standard error of the mean, which would be the sample mean, like we did in Stat 100, right? The mean divided by the standard error, the mean over square root of n. We'll go into that later, but you pick a statistic. So then, and you check how likely it would be to get the test statistic, or one even farther, if the null were true. Why don't we just, let's do a picture's worth 1,000 words, right? So let's just jump right to it. So for example, for this thing, what would you say? Okay, so we have H naught would be what? That the difference between the two averages is equal to 0, right? The difference is equal to 0. And the alternative would be what? The difference is not equal to 0. That there's either the online or the in-person group is doing better. All right. So if you're used to more formal language, we can look at it later. What would we'd be saying what? That in the population, which we call the Greek letter here, don't worry if you're not. This is for people who've already had this. If you're in Stat 100 and haven't looked at this, don't worry. We'll get to this later. But basically, it's the average of the online minus the in-person, the L1 section, or vice versa, it doesn't matter, is equal to 0. And then the alternative is that this difference, this idealized population, is not equal to 0. We just happen to see a sample difference, right? So we would we'd come up with a test stat. And since we're talking about the mean here, our test stat would be z. And we'd say, OK, in our sample, we have some observed difference. Right? In our sample, we have an observed difference. Let's say there was a difference of a point or something between them. And we expect the expected difference under the null is 0. So we'd have that. And we'd compare it to what we'd usually, the difference we'd usually expect, just by random sampling, which is called the standard error of the difference. We've computed that many times. We'll show you how to compute it later. I don't want to get distracted. But this has a known sampling distribution. And the sampling distribution under the null, because of the central limit theorem, and you've all seen this, is our old friend, the normal curve. So what this means is that if you did this over and over and over and over again, right, and compared, took a difference, there's 300 of you in here, right? Between this, there's more. There's 170 in one class and 170 in the other. So you have 340 students. Imagine putting all the test scores in a box. This would be our probability model, in a box. And then take a random division under the null, random division of the two sets of the scores. So randomly divide them into two groups, 170 in each, and take a sample, take the average, right? Take the average of the two groups of that sample, and we'd expect it to be 0. But is it always going to be 0? Do you think it's going to be 0? No. So how much, just by random variation, would it vary? And that is the standard error of the difference. And when you translate it into a z-score, this difference, what you'd expect to see just by chance variation, divided by what you typically see, which depends on the spread of the scores and the sample size, right? You get a beautiful normal curve like this. This is the central limit theorem under certain assumptions, right? And it looks like this with what? That 68% of the time you expect to be here. 95% of the time, you expect to be approximately within 2 standard errors. And about 99.7% of the time, I think it's 73, you expect to be within 3 standard errors. So what you do is you say, OK, you look, you translate whatever difference this is, and it would be the difference between the sample, x bar instead of these are these Greek letters for the ideal and the Roman letters for the ordinary of the sample on line. It doesn't matter which direction we're going in, because we didn't specify that one's going to do better than the other, okay, over the standard error of their difference. So if we saw 1 point difference, we'd say 1 point divided by the standard error. We translated it to z-score, and that's different than these. This is without any units. These are these beautiful unit-free, and we translate that actual difference and put it somewhere on here. If the online did better, it would be up here. If the in-person did better, it would be down here. So it doesn't matter, and we're just seeing how far outside it is, right? How far. So if it's way out beyond it's very, very unlikely. We say there's some systematic difference. So that's the idea. And you call that the P. So now let's just go back to our notes. Any questions on this so far? All right, so let's go back to our notes. And we'll say, check how likely it would be to get our data's test statistic or one even farther from the null if the null were true. That's called the p-value. So let's say it was, we translated it, and it was way out here somewhere. Let's say it was right here, right there. Well, between -2 and 2 is 95% of the curve. So our p-value, because we didn't specify direction, would be 5%. Because 2.5 would be here, and 2.5 would be, this is 95% between 2 and -2. And then we'd say, OK, what's the likelihood of getting this far out when the null's true? Is this enough evidence to say there's a systematic difference? And we'd say, How often does that happen? Well, it would happen here, this direction, this would be that far away. So this would be a two-sided test, and it would be a p-value of, what did I just, oh, here, of 2.5% here and 2.5% there, which is 5%. If we had thought this group was going to do better to begin with, and it specified that, we would have had that the difference here in this regard would be less than 0, and we would have a one-sided, a smaller p-value. All right, so that's the idea. Let's read on. All right, so now it says, okay, if the p-value is very low, we say the data supports rejecting the null hypothesis, and it's unlikely to be due to chance. Well, how low is very low? The convention is to reject the null when p is less than 5%. That's just a convention, and call the result significant. And when p is less, this is a convention, and people go by this, so we might as well highlight it, because that's often what people say. And when p is less than 1%, the result is called highly significant. Now, this is an important point that people might not emphasize, that there's no particular justification for those p-values. They're just very commonly used. Look, if you're looking at, it's not like there's a cliff and all of a sudden at 5% or something, it falls down. No, do you really think there's a difference between here and here? It's arbitrary. Why 5%? It's just arbitrary. It's probably just because, we're in base 10 is a nice real round number, 5%, instead of 6% or 4%. But people, if you're going to do this test, people like a cutoff. They like to say, okay, I'm cutting it off here, and if I see this much evidence, but the curve is much more informative to report the actual p-value and not if it's significant, and pay attention to the actual p-value. What I mean is how far out away from what you'd expect, how unlikely it is to calculate that, and you decide whether it's significant or not. That's much more informative, even if you're using these cutoffs. Don't lose that information. Okay, so now where are we? But that's called a significance level, and it's often set ahead of time, especially in calculating what sample size you need to achieve a certain power, which we're going to talk about later. Now, the significance level is the probability of mistakenly, this is really important, rejecting the null when the null is true. It's called a type 1 error. It's really just, we set the significance level to be low to keep the chances of making a type 1 error low. Why is that an error? Because this is the sampling distribution. I'll write it here. This right here is the sampling distribution of what? Of the sample difference, the difference between these. Ooh. Hey, am I upside down? Probably. Like crazy. Okay, there you guys are. All right. Hey, there really is real people here. Okay, yeah, wave. Hey, see, come join us sometime. All right. So now we're back here, and I said this is the sampling distribution of what? The difference. This of the averages when the null of the difference when the null is true. When the null is true. So when there's really no difference, a random division will result in this. So if we reject it, hey, the null was, this is the percent of times we're wrong because the null was true. Okay? Maybe I should make this really vivid to you. I'm just thinking about our own data. Okay, so it's not going to, unfortunately, I don't have it as a normal curve on our point-and-click data program, but let's look at what I mean by a sampling distribution in these p-values, okay? So let's just take a break here to look at, this is our Stat 100 data between the online and in-class last semester. So yeah, R is super valuable, but boy, this data, this point-and-click data program developed by our resident genius, John Martin, who's a statistic professor, retired, is just unbelievable in exploring the data. So let's just choose a data set, and we have lots of data sets here. So I just want to see what this looks like. So let's look at, it's going to be our Stat 100, spring 2017 data. We've already done this, a slight variation on this in Stat 100 last semester. We've been doing this for a year in Stat 100, collecting data on this, where there's an online version and it's basically the same deal as what you're going through now. Okay, so we've got data on this, and so what should we do? So let's first look at histograms and box plots. All right, so why don't we just go to the end of the course. Course total with bonus. This is what your grade is going to be based on, all right? So this is going to be a numerical. This is what you get at the end. So let's look at that. And this is the Stat 100 grades, and we want to split. We want to choose a split, and we want to split on the section between the, this is, more people took the in-person, this is the online. So that's the split we're going to choose, and we'll split the plots right here. And here's the stats. They look very similar. And here you can see. Okay, remember there's always going to be some difference, right? Always. It's not going to, if you take it out to enough decimal places. So here's the difference we got. And I'm very happy that there's very little difference. We hope there's not much difference. You know, we don't want like one to be, what we really want is to identify which subgroups do better. You know, that the overall, there's not much maybe, but which, all right, another, maybe a easier way to visualize this, or another way, is looking at the box plots, and you can see that the online has a slightly different box plot. This right here is the median, not the average, but it's just another way of visualizing it. A third way of visualizing it that we could look at would be the scatter plot. So if we went to the scatter plot and we chose the x variable as section, which section you're in, and the y variable is course total with bonus, and then here are the averages, and if you draw a regression line, it looks pretty flat, but there's a slightly very small correlation coefficient here. And what's this? What is this saying? This is saying that the difference between the two sections, this was just coded as 1 for in-person, 2 for online. So as you go, just that one, you know, it's just, it says as you go from one section to the other, the difference is 0.8392. We saw it was 0.84. This, we rounded it to 0.84. So that's the difference between the two sections. And is that significant or is it not? Well, we can, and you can look at, well, we could look at another way of doing this. Let's go here, and we'll choose the variable class total with bonus, right? And here we have the course total with the bonus for the in-person and the online class. And again, we see this 0.84, this 0.84 difference, and that should be the same correlation coefficient. Is that the correlation coefficient? Let's just quickly check back. Remember that 0.04233. I think that's exactly what we got when we actually looked at the scatter plot, and we pick section and course total, and yes, there it is. So, so that's so let's go back to the. So there's all different ways of analyzing this, and if you do something called a two-sample Z, or which is equivalent to a chi-square test, it gives you this R, which is the correlation coefficient that we just saw. And so we can look at the sampling distribution of this, do a simulation of it. So right here we see this P. What does this p-value mean? All right. Well, this is the likelihood that we'd see such a difference, this difference of 0.84, just by the luck of the draw, right? If nothing's going on. And it says there's, you know, that's not, so if we were using our usual 5% cutoff, we would not reject the no. This looks like this difference is just due to random chance, right? 10.65% of the time it's going to happen just by the luck of the draw. So we can actually enact the luck of the draw and do a, now this is just the positive R. So it's grouping the negative and the positive together. And we can do a re-randomization test. And this is actually doing exactly what we talked about. It's putting all 1,452 of the people of the scores together, let's say, and then looking at each time. Right here, it did 1,000 randomizations, and each randomization is randomly splitting up the 1,452 scores, each score representing a student's overall average at the end of the semester, into two groups, and seeing how likely is it to get this big a difference. So here, I'll show you what it looks like. And here's a histogram representing those 1,000 randomizations, and we'd expect to get 0, right? But we don't always get 0. Now, why isn't there any? And what does this line mean? This line represents the actual sample that we only see when we do this experiment. We only see one sample, so that of the 1,000, we only see one of them. And this represents where we lie in this distribution. So the 10, what does it say? Let me just uncover this. This 9.4%, what is that? Well, that's the proportion of the 1,000 samples that actually got even more extreme evidence for rejecting the null, that we actually, just by random division, we got an even stronger difference between the two samples in their averages. So a bigger correlation. And why, you might ask, why doesn't it look more like the normal curve? What happened to the other half of it? Well, this statistic is giving both the negative and the positive values. It's only showing, it's the absolute value of R. So all the negative values are just, it's the absolute value. So you just see half the curve here, basically. So, so here it just seems like, okay, basically the two, the overall, it doesn't seem like we have much evidence that anything besides random variation is going on, and we'd conclude that the two courses basically are equivalent. That, it doesn't look like either teaching method is more helpful than the other one, right? Is that it's basically just chance variation, any difference we see here. That's what we'd conclude. As opposed to, let's look at other, maybe let's look at something else here, like the final exam score, okay? So if we look at the final exam score, now we see this difference here of about 2.5 points, right? And if we actually computed a z-score and did it, we'd see a very significant here. This means that it's very unlikely that this difference is due to chance. That when a random division only results in a difference this large, 0.02% of the time. So if we actually enacted the experiment and did the simulation of a random division into two groups here of size 999 and 453, and we did a histogram. Let's look at this. We said, what does that 0 mean? It says, okay, so this histogram represents the 1,000 randomization. Each time computing a correlation coefficient, think of it as a difference between the two sample averages. And this is what we actually got right here, 0.09575. And it looks like it's extremely, just by chance variation, we have not gotten that. And that's why we have 0% here. Let's do more randomizations. Let's see if we eventually do get something. So we'll do some more randomizations. This is 2,000, 3,000, yeah. Okay, so here's 4,000 randomizations. Now what does the graph look like? Do you see that one of those, or just now we have I'm not sure how many that is, but we have 0.025% of the 4,000 randomizations actually getting as big a difference, as strong a correlation between the online and the, between which section you're in and your exam score as our sample. So that's the idea, and this seems to, we can do more. So we'll do more re-randomizations and more and more and more. See, each time this is an actual, this is a simulation. It's not done analytically. Let's look at it now after 41,000 randomizations. It's a smooth curve, and the likelihood that we'd see a difference is large between the two sections in final exam scores is the one in our sample is very, to get a difference that big or bigger is very small. It's only 0.0122. So so we could look at other statistics here too, but that's the idea of what a p-value is. Now, of course, people weren't randomly assigned to the in-person or the online class. They chose. So the teaching method wasn't the only systematic difference. All a p-value tells you is the likelihood of the difference of a difference you see being due to the luck of the draw. And clearly something like this, in this case, the difference in final exams is clearly not due to the luck of the draw. I mean, it's the likelihood that it's extremely rare just by the luck of the draw to get this. So that means there's a systematic difference, but it doesn't necessarily mean that that systematic difference is the lecture delivery style, because the students chose themselves. So it could be something, there's a systematic difference between the type of people who might choose the online versus the type of people who might choose the in-person who could be causing this. So this is the type of thing we're trying to figure out looking at this data. Now you can also look at other data here. For example, you can look at the bonus points. Or you can look at the homework average. Why don't we try that? So now we're looking here, and that says, okay, so there's a small difference, very small difference in the homework here of what? 0.49, almost 0.5 difference, but the p-value is huge. That means what? This p-value means this is the percentage of times you'd see this just by the luck of the draw. That's what that p-value represents. That this whole curve is 100%, remember, because we're just taking the absolute value of r. So if it went in this direction, we're just looking at half of it. And I mean, we're looking at basically the equivalent of a two-sided z-test. And yeah, that's an enormous amount of the time that's just going to happen by chance variation. So we can't say that that's a systematic difference between the two groups. So that's the idea. R. All right. So I can see people are getting antsy. Let's do it. All right. So we talked type 1 error. So what is it? We have this thing. Let's just remember. So we have this curve right here. We're looking at the normal curve right here. And we have this type 1 error. And so this is when the null is true. We have the sampling distribution. And let's see, it's right. Let's say we have the cutoff right here. We set some significance level. And we call this alpha. And this is a type 1 error. And basically, it's a mistake, right? It's like a false alarm. Nothing's going on here. Let's think of it that way. Let's say this was some smoke detector. And this right here, this axis, is a quantitative measure of how much smoke is in the air. Well, the null is that there's no fire. So this is the times the smoke alarm goes off, like when you're cooking and it's not a fire, it's just wrong. Happens to me all the time. It's annoying, but it's not that serious. But that's the type 1 error right there. And we set that. When you're making the smoke alarm, they actually set it about, in my house, they seem to set it here because every time I cook, it goes off. But that's what we set. So we set the problem, when you're making those smoke alarms, we set alpha. And that is the probability of the type 1 error. Okay, but now we have to remember, what if there really is a fire? So this is when there's no fire, when H naught is true. This is the, some measure of whether, quantitative measure of whether, when there's not a fire, right? And it will go off at some point. But there's another type of mistake we can make. Let's say the null is false if there really is a fire. Now I'm using this very simple example where there's just one alternative. Fire is the alternative. It's not like measuring how well the online class versus the in-person class goes, or how well a drug works, what percent of the people cure. We're just saying it's an all or nothing. Like, do you have cancer? Do you not? Are you pregnant? Are you not? It's just measuring it when there's one alternative. Simplest case. All right? So when the alternative is true, when the null is false, then we'd like our significance test to correctly reject the false null. So a type 2 error happens when the null is false and the test fails to reject it. So let's draw that picture. So when the null is false, that is when there really is a fire, when the alternative is true, and there's only one alternative here, we are going to have another, it's the same measuring device, but of course there's going to be more evidence for a fire. So it's going to maybe look something like, oh, I don't know, something like that. Let's say it looked like that. It's supposed to be, a similar distribution. Let's say it looked like that. Okay? Now, if we cut off, what's the type 2 error? So this is our decision making. We've decided to set alpha right there, 5% type 1 error. Well, when there's really a fire, let's just say fire, yikes, and this is nothing. No fire. What is this mistake doing? There is a fire. Now, sometimes there might not be strong evidence for it. A smoldering, like you don't see much smoke. So we are going to say, this is when we fail to, the smoke alarm didn't go off. This is a type 2 error, which in this case is deadly. And we call that beta. So that's our type 2 error. Okay? So that's the idea. And let's see, where is it? Type 1 error, and here's our type 2 error. Ta-da. And so when it's exactly what I said. The null is false. This is false, the alternative, and our test fails to reject it. It didn't. This is rejecting the null, right? Okay, so the probability of making a type 2 error is called beta, and the power of a test, which is super important in designing stuff. The power of a test, it's a very important measure. The power of a test is the power to detect a difference when it's really there, right? You want really strong power in this case, right? And the power of a test, this is whole thing. This is the mistake. It's 1 minus beta. The whole curve is 100%. We'll call it 1 or 100%. So the power to detect a difference when it really exists is 1 minus beta. So this would be the power. All right? And so does this make sense? Any questions on this? Okay. So we have beta, we have alpha. This is a probability of a type 2 error. This is a probability of a type 1 error. And the power is 1 minus that. Okay. So let's see. So maybe a chart will help. Now this chapter 1 and your homework on chapter 1, which I'll post soon, is all in the case where you have this very simple one alternative. You don't have to specify an alternative. Most of the time when you talk about power, you have to specify an alternative, like how many people do you want the drug to save? Like what's the biggest difference you're interested in? For our online versus in-person class stuff, it would be, do we even care about a 1-point difference or not? Or what's the smallest difference we care about? Maybe we do. If it's in terms of saving lives or something, then like a 1% reduction, if it's a very common in death rate, and if it's a very common thing, lots of people get the disease, well, that would be huge, and we'd really want to detect even 1%. In terms of, I don't think a 1-point difference makes much difference, but if it was a 5-point, what's the smallest difference you care about detecting? And you want enough sample, enough people to be able to detect that difference. All right, that's chapter 2. But for now, there's just one alternative. Okay, so this is super, super simple. So here's a chart. Maybe this will help. And so here you have some truth. You're making decisions under uncertainty. You have the truth and you have a decision. You want them to agree, of course. So when H naught is H naught is true, that means nothing's going on. There's no effect, nothing. No effect, and we just think of it, I don't know, like on a negative. You don't have the disease, negative for fire, no effect. And H naught is false means that there really is a real effect. So we'll call that positive. So that's the truth, right? So if there's no effect, and we reject the null and say, that's a false alarm, right? So that's a type 1 error, and that's what we just saw. That's our type 1 error. That's this, right? And again, if there really is a fire, and we failed to reject the null, our alarm didn't go off, well, that's the type 2 error. And there's power, and this is something nothing's going on, and we didn't say anything was going on. It's just run of the mill. All right, so let's skip around. Let's do another one that I'm involved in all the time, which is catching cheaters. They either cheated or they didn't cheat, right? So again, it's just did they cheat or it's one alternative. Like, do you have cancer or do you not have cancer, etc. Okay, so let's look at this. So either the person is guilty or the person is innocent. And we have this detection system like here. So when the defendant is truly innocent, now it's not really a quantitative detection system, but kind of. I mean, if proctors at all these exams, we look at those. Sometimes we have film, we look at how many times the person's eye wanders, like how many questions, or let's say, there's a lot of data we have that's not perfect, right? Sometimes if they copy down all the answers or if they copy down work or something, it's more or less, we can catch them, but often it's nebulous, and certainly in other classes it's often nebulous, right? So so we say, okay, so this is whatever measure we're to determine whether the person cheated or not, and we say, okay, well, all right, let's say at this point we say we have enough evidence beyond a reasonable doubt. It's like our jury system in America. Beyond a reasonable doubt, you assume innocence. And so this right here is your type 1 error, right? And then when the people are really guilty, well, we're using the same detection system, but some people are so slick and they don't get caught, right? Some people are really slick. So of the people who cheated, well, this is our type 2 error, right? So you might say, well, why don't we just make this so small? Why don't we just so that we never, ever accuse, people get kicked out of this university for cheating. So I am a softie. I want to make this move it over, and I have, until it's basically, it would be almost impossible for me to kick out an innocent person. But then what happens if I slide that over, so they'd have to have overwhelming evidence, right? Then what you end up doing is what? You end up having, yes, almost no people that you've innocently kicked out of the university. But on the other hand, you have rampant cheating. You have all these guilty people who are running around and ruining the fabric of the class. So I face this. I've taught since this first started teaching Stat 100 in 1983. True. Finally, I got it down where I changed. The other thing you can do is change your detection system. So you come up with a much better test. I don't do this anymore. Just look if people's eyes are wandering and all that stuff. No, I have a different way of doing it that's nearly foolproof. And that has put then the measuring stick is a very good detection system, and you don't have all this uncertainty. So that's the solution we came up with. So that's the idea, but we're not, usually that's not possible to do. All right. So I think this is pretty much, we're doing the summary of the reasoning here. And this is the chart for, I guess let's just fill this last chart in. You're so antsy to go, but I want you to read the summary on your own. Read the summary on your own, for sure. Read this all on your own. And basically, you have a truth out there, and then you have a decision. And you want them to agree, right? So this is just a way to set it up. You think that when the null is true, that's nothing that's going on. And, just pretty much, we don't say accept the null, which would be really easy, but because we're assuming it to begin with, right? We haven't proved the null, that nothing's going on. We just don't have strong enough evidence to reject it. So we don't, so we have no effect here, and that's fine. And then when there is a real effect, we want to say there's a real effect. We reject the null, and that's the power of the test. And that's basically the setup. So I'm going to let you out early so you have a chance to talk to, come up and talk if you have any questions, and see you next time. I'll post your homework.